Hello. In this video, we're going to continue to develop our understanding of function notation. Now, in the last video, we didn't do a definition of functions, but what we did say was that a function is a special type of relationship. And mathematicians have been interested in these types of relationships for a long time. But it was in 1748 when one mathematician named Euler wrote this: y equals f at x. And what it was a new way of writing y. Now I'm going to tell you two things for the sake of this video. First thing is, all linear relationships are functions. And secondly, all quadratic relationships are functions. So you might not be familiar with quadratic relationships yet, but I'll show you one in this video, and we're interested mostly in the algebraic manipulation here, not actually graphing them. So let's do an example question here. So if f of x is equal to, let's say, 3x minus 2. And now, before I continue this, here's the thing. Let's say I want to talk about another function that's different. I want to talk about a function, say, x squared plus 4, which actually is a quadratic relationship. And that's because of the squared term. Though I could call this f of x, it gets a little confusing because if this function's called f of x and this function's called f of x, if I ask you to solve, say, f at 4, the question comes, well, which one do you want me to work with? So here's the thing. The reason we use the letter f is because function notation was developed for functions. But we can name functions anything we want. I could call this function g. So in this question, we have two functions. We have function f. So f of x is 3x minus 2, and we have function g. So g of x is x squared plus 4. And now I can distinguish between those two in my notation. Common letters used for function notation: f, g, h. You'll see a whole bunch of them. So let's continue. If f of x is 3x minus 2, and g of x is x squared plus 4, find. Let's put a couple here. So let's say f at 1, let's say g at 7, let's say f at 2 plus g at 7. It's a little tricky. And let's say f at z minus g at z. Okay, so let's do these problems together, shall we? So all this means is we just simply take function f and we substitute 1 for all the x's. So 3 times 1 minus 2. 3 times 1 is 3, minus 2 is 1. So f at 1 is 3. That means on the graph we have the point, f at 1 is 1. That means on the graph we have the point 1, 1. Let's do this one. So g at 7 is equal to 7. And I really like to encourage the brackets there, because sometimes if you don't put brackets in your substitution, you can have some problems. 7 squared is 49. 49 plus 4 is going to be 53. So g at 7 is 53. So therefore, the graph g has the point 7, 53 on it. Again, you don't have to write this last step, but I'm just trying to reinforce the idea that f of x, or g of x, is just another way of writing y. So this one might give some pause, but if we break it up, it's not that hard. What we're doing is we're finding f at 2, and then we're finding g at 7, and we're adding the results together. So sometimes students like to do this when they first get a problem like this. They'll actually break it up. 3 times 2 minus 2. 3 times 2 is 6, minus 2 is 4. And then they'll work out g at 7. Well, look at that. We already actually worked out g at 7 over here. So we know that's 53. So therefore, f at 2 plus g at 7 is equal to 4 plus 53, which is equal to 57. So now this is the one that always gives pause, because the student will say, wait a second, there's not a number in here. But the rule is whatever is inside the brackets here gets substituted in wherever the x was. So here, instead of x, I have z. So what I simply do, and we'll do this in 2 steps, f at z is equal to 3 times z minus 2. Now let's do g at z is equal to, well, z squared plus 4. So in this question, we're interested in f at z minus g at z. And watch here, this minus sign can be a little tricky. So when you substitute in, this is a place where brackets are going to help. So f at z is 3z minus 2 minus, and now I'm going to substitute in the function g in brackets. So bracket z squared plus 4. And when I do that, I catch the fact that I have to actually distribute this negative across the brackets. And now I want to simplify. And I will tell you a little etiquette piece when you're working in mathematics is you always want to write your highest power on the left. So negative z squared plus 3z, and then minus 2 minus 4 is minus 6. So f at z minus g at z is minus z squared plus 3z minus 6. So just to wrap up, remember, function notation is simply the process of replacing y with f at x. But if we want to name a function something else, we can call it g of x, h of x, w of x. It doesn't matter. It is a way that allows us to communicate in a little bit more of an efficient manner, and especially later on we start getting to more complicated cases. A last point is that notice in example C and D, I've kind of broken it down to steps. Students will have to say, well, can't I just jump and do this right away? And the answer is sure, of course you can. But the one thing I like to remind students is that, remember, let's talk about tests. I'm not a big fan of tests. I find tests, that's a whole other discussion. But if you jump down to this on a test and make a mistake, you're not showing me where that mistake was made, so it's harder for me to understand your thinking. And as a teacher, what I want to understand is your thinking, and if I can see where you've made that mistake, that means you've communicated a better understanding possibly. So remember, though you don't have to show every step, in a testing situation, it's always good to show a few more steps because that helps clearly articulate what you're thinking, and therefore if you make a careless mistake, your teacher can see that. I hope this video helped.